Okay, so let's start. This is part of the water process integration topic, and this is the part 4, or the other extensions for water minimization. Okay, so remember this diagram. I think I have shown this to you before. So the past topics on water minimization, we focus on either reuse or recycle. Um, I think in our examples, we did recycling of the waste streams. But today, this topic, we would focus on regeneration, reuse, and regeneration recycling. Again, what do we mean when we regenerate a stream? So regeneration is where we use a purification method uh, to purify the stream before it's used, say, in another unit for regeneration reuse, and for recycling to the start of the process in regeneration recycling. Okay, so this is our example before for the AN production. And remember that we did a pinch analysis for this case study, and what we got is for a freshwater, um, we were able to save on fresh water, and we only need 2.1 kilograms per second of fresh water, and then the wastewater total is 8.2 kilograms per second. And then we also were able to know the values of the recycling streams, wherein we're able to recycle 6 kilograms of water into the scrubber. So you should remember this. Okay. So, this is the pinch analysis of that. Oh no, this is a different one. Uh, this is different because we're going to try to, okay, regenerate part of the waste stream. So before, what we did is we all of the waste stream went to the treatment unit, and then after the treatment unit it will be released to the environment. But now we will regenerate part of the waste stream, so that means it will undergo purification. Some examples of purification processes can be membrane absorption, ion exchange, distillation, anything that can purify the streams. And then once we do that, then we can cut down more of the freshwater requirement. Okay. Now the challenge is how to find the right units, and how big is that unit of regeneration process. Okay. So this is, so by the way, if we recycle it, or we regenerate part of the waste stream, then we have to use now this impure fresh locus um, diagonal in our pinch analysis. Okay. An example or an option here is to make use of an absorption column. Say for example, we focus on the waste from the off-gas condensate, okay, so that it can be purified from, initially this is, it's not shown, but this is 14 ppm of ammonia to 11.6 ppm. And so you can see that um, initially we have uh, so the mass flow rate, okay, initially we have, nasaan na ba yan? Wait. Okay, so remember last time we did a balance on the flow rates, and we're able to determine how much recycling we can do. So right now, uh, with the absorption column, we can try to regenerate 4.6 kilograms of water per second. Uh, so if we do that, if it means that we can completely cut off the fresh water going to the scrubber, and we can completely rely on recycled and regenerated water for the scrubber. So from the bottoms, we have 0 ppm of ammonia. So this is recycled. And then we have regeneration that has 11.6 ppm. So we're able to um, completely remove the stream. So I'll just go back to the previous slide so you can see that before we have freshwater stream also going to the scrubber, but because of regeneration, we're able to fulfill okay, the requirement of 6 kilograms um, of water per second. Okay. Now, if you want to cut down further the freshwater requirement, we can completely, okay, get rid of this part of the process, which is the steam injector. Alright, because it utilizes fresh water. So if we do that, for example, we completely remove that. What we can do is, for this example, replace it with a vacuum pump. Okay, so replace it with a vacuum pump. So before, uh, the top of the distillation column would proceed to this injector. But with further reduction, say we really want to remove the requirement for fresh water, then what we can do is to just replace it with a vacuum pump. So we can also suggest this to the industry. Okay, if for example we're consultants. However, it will entail additional capital costs. Of course, it will entail retrofitting of the current process, removing the old section of the entire process, and then investing in a vacuum pump. So we can do that if there's a regular shutdown in the plant. However, it's difficult to do this when there's continuous operation. So in terms of priority, we call this process changes. Okay, process changes. Uh, so we modify the process like to remove the inherent usage of fresh water and to remove the wastewater generation. Okay, so again, this one, installing an absorption column is also a process change, as well as if we remove a section, that's a process change. And it requires investment on the part of the industry. So we summarize our proposed solutions to the problem in this graph and in this table. So in the original case study, the freshwater requirement is 7.2 and the wastewater is 13.1. When we did the recycle and reuse last meetings, our freshwater went down to from 7.2 to 2.1, and our wastewater also went down to 8.2. With the regeneration, by installing an absorption column, we're able to further reduce the freshwater requirement and also reduce the wastewater requirement. And further changing the process by removing an entire section of the process that requires the freshwater, we're able to really cut down on the freshwater requirement to zero, okay, and also the wastewater requirement. So this figure just reflects the numbers here, and the x-axis shows the different strategies, while the y-axis shows the flow rates for each freshwater, wastewater, and the savings. So as you can see, uh, in the last strategy, the saving is 100% because there's already zero requirement. So the saving for freshwater is 100%. There is a hierarchy in the water saving. Um, so we have the low hanging fruit. Are you familiar with that term, low hanging fruit? Is the water reuse and recycle, which is what we did in the past lessons, because it is low cost and low impact compared to the other steps or other strategies. The next strategy is installing a regeneration or purification unit. In terms of cost, uh, there is cost because uh, you have to invest in the adsorption column. And finally, the last strategy, which is the highest cost and impact, are the technology changes. So, of course, the cost is bigger because you need to invest more on the techno or process changes. In terms of acceptability, if you're the business owner, of course, your first option or your first choice would be the water use and recycle, and your last option is the technology change. And a typical water saving, if we do this analysis on a typical um, plant for refinery, chemicals, pulp and paper, and food and beverage, the typical saving is between 25 to 40%, which is big. Uh, Even if it's not 100%, if we translate this to the actual numbers, is a good number or a good benchmark already for the water saving. So, for example, if you want to be a consultant, wherein you're recommending uh, resource savings or focusing on water savings, if you achieve this, then it's already acceptable. Okay, so that actually is the end of the topic on process integration for water minimization. Okay. Do you have questions, Crystal?
Wala naman po.
Okay, so I'll stop the recording.